This is the Chapter 17 lecture outline. This chapter will be split into two as per usual. This chapter is going to cover moisture, cloud formation, and precipitation. Okay, first topic in Chapter 17 is the changes of state of water. So we already talked about how heat energy is transferred, but how do we actually measure it? Well, we measure it with the unit of calories. So 1 calorie is the heat necessary to raise the temperature of 1 gram of water by 1 degree. So this is very closely related to that topic of specific heat that we mentioned in the previous chapter. I will mention one thing about temperature. If you're wondering what exactly that is, it's simply the measure of what's called the kinetic energy of a substance. So kinetic energy is associated with the motion of particles. So how fast the molecules in a substance are vibrating, so how fast they're moving, is actually what we talk about when we say temperature. So if we add heat to a substance, we're simply just increasing the rate at which the molecules are moving. You can even think about it as a vibration if the substance is solid. Okay, so we also have latent heat, which is just stored or hidden heat, and this is not derived from a temperature change, but it's important in atmospheric processes. So we have three states of matter: solid, liquid, and gas. And to change state, heat must either be absorbed or released. So we have different processes to change from one state to another. We have evaporation, that's liquid to a gas; condensation, water vapor, so a gas to a liquid; melting, solid to a liquid; and then freezing, liquid back to a solid. We do have two special processes called sublimation and deposition. Sublimation is going from a solid directly to a gas, bypassing the liquid phase. And then finally deposition, which is going directly from a gas to a solid, bypassing the liquid phase. On these two slides, I'll go back one. There's numbers on here about so many calories per gram to have these changes. You're not going to have to worry about knowing these numbers, but do know what each of these processes mean. And this is a nice graphic that breaks down those changes in state for water specifically. All right, moving on to humidity. So I mentioned before in chapter 16 that humidity was simply the amount of water vapor that's in the air. So saturated air is air that is filled with the maximum amount of water vapor that it could possibly have. So we say it's at capacity. And capacity is temperature dependent. So warm air has a much greater capacity to hold water vapor, where cooler air would have less of a capacity. And water vapor adds pressure, called vapor pressure, to the air. So how do you measure humidity? First thing we need to know is the mixing ratio. This is the mass of water vapor in a unit of air compared to the remaining mass of dry air, and this is often measured in grams per kilogram. We also have relative humidity, which is ratio of the air's actual water vapor content compared to the amount of water vapor required for saturation at that temperature and pressure. So how do you measure relative humidity? So this relative humidity is typically expressed as a percent. In saturated air, this means content equals capacity, so it has a 100% relative humidity. And relative humidity can be changed in two ways. You can add or subtract moisture from the air. So adding moisture raises the relative humidity, removing it lowers the relative humidity. It also can be changed in two ways. You can change the air temperature. If you lower the temperature, that raises the relative humidity. We also have something called the dew point temperature. This is the temperature to which a parcel of air would need to be cooled to reach saturation. So cooling the air below the dew point will cause water vapor to come out of the air, and the process of condensation would come into play. So this is how you would form dew, fog, or even how clouds form. So water vapor requires a surface on which to condensate. The next two slides I left on here, but you're not going to be responsible for knowing any of this math for the quiz or exam. I just left it here as good examples on how to figure out if a parcel of air is saturated, and then how you can actually decrease the temperature of that parcel of air to reach a relative humidity of 100%. All right, so how do you actually measure this humidity? So there's two types of devices. One is called a psychrometer, and this compares the temperatures of two different thermometers, one attached to something that's wet and the other that's dry. And the other type is a hair hygrometer. It reads the humidity directly. So here's a picture of a sling psychrometer. So you're going to see on either side there's two thermometers, and then the one side there's a piece of cloth that can be put into water to make it wet, and you're measuring the temperature differences between the two thermometers. If the temperatures of the two are the same, that means you're at a 100% relative humidity. All right, so we're starting to get into the part of chapter 17 where it talks about cloud formation. So the process by which cloud forms involves adiabatic heating and cooling. So adiabatic temperature changes occur when air is compressed. So this is when the motion of air molecules increases, when the air will warm and descending air is compressed due to increasing air pressure. Air expands, that's when air will cool, and rising air will expand due to decreasing air pressure. So we have something called the adiabatic rates, which basically say how much the temperature changes per altitude. So the dry adiabatic rate refers to unsaturated air, and rising air expands and cools only at 1 degree Celsius per every 100 meters. So descending air would be compressed and warm at that same rate, just in the opposite direction. The wet adiabatic rate commences at the condensation level, and when air has reached the dew point. Condensation is occurring and latent heat is being liberated at this when the wet adiabatic rate takes over. So heat released by the condensing water reduces the rate of cooling. So the rates vary from 0.5 to 0.9 degrees Celsius per 100 meters. So the rate's a little less when we're talking about the wet adiabatic rate versus the dry adiabatic rate. So how does this work? Well, we're interested in forming clouds. So as air rises, you're seeing that the temperature is going to cool and cool as you get higher and higher in the atmosphere, specifically in the troposphere. And then once you hit the condensation level, the air is going to become 100% relative humidity. And then after that point, we're going to start forming clouds. And the stuff that clouds actually form on is just dust and different types of pollutants that are in the atmosphere. And then once you reach the condensation level, we're going to start condensing water vapor onto dust, forming clouds. And then at that rate, the adiabatic rate takes over and we start cooling a little slower than when we were cooling before the condensation level. All right, the last part of Chapter 17, Part 1, are going to describe different processes that will lift air, allowing clouds to form. So the first two types are orographic lifting and frontal wedging. Orographic lifting is when the actual geography of a region, so in this example, you have air parcels, an air parcel coming from the coastal region of an area, and then the air is forced up into the sky, so increasing in altitude once it reaches this mountainous region, and that uplifting of air due to the mountain will cause the temperature of the parcel of air to decrease, increasing the humidity until you reach the condensation level and clouds will start to form. And then on the other side of the mountain, if the air were to drop down in altitude, it will become much drier and you can have something called a rain shadow desert forming. The other process mentioned on that slide was frontal wedging. We're going to talk more about frontal wedging when we talk about severe weather patterns and storm systems, but just understand that this is when a cold air mass is going to be moving into a region where there's warm, moist air. So that cold air mass is going to act like a wedge and lift that air up into the atmosphere and increase in altitude. And when that warm, moist air increases in altitude, you're going to reach the condensation level and form clouds. And specifically, when a cold front meets a warm front, that's when you're going to have severe weather. So you would form clouds and lots of precipitation. The last two types of processes to lift air would be convergence and localized convective lifting. So convergence, the easiest example is to talk about Florida, where you have air parcels coming from the Gulf of Mexico and more air parcels coming from the Atlantic Ocean. And when those two air masses converge, the only direction the air has to go is up. So the air lifts up in the air, higher altitude, lowers the temperature, increases humidity until it reaches the condensation level, and then clouds are formed. So that's why in Florida, on any given day, you can have severe weather happening all the time. And then the last type is localized convective lifting, and this tends to happen a lot during the summer months. You're going to have some warm, moist air in the mornings during summer months, and then the solar heating throughout the day it's going to cause that air to rise, and then once that air rises up to the condensation level, you're going to have clouds created and you can have localized storms being created during those months.